Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, lecture 93, standing waves. So what exactly is a standing wave? And if you've ever looked at a guitar as it's playing, you'll see what a standing wave is, right? It's a wave, looks a lot like our traveling waves, except it's not moving. If you imagine riding in a car next to a traveling wave, right, such that it looks, for the most part, stationary, except for the up and down part, right? Everything kind of looks like it's going up and down, but you're traveling along with it. That's what it would look like if you were following a standing wave. Excuse me, a traveling wave. It would look like a standing wave. So a standing wave is fixed, right? And how do we fix it? Well, we fix it between 2 points usually, right? We'll call this the left end, this the right end, okay? And so we can imagine taking a piece of string, tying it taut across these 2 points, right? And then plucking it, right? Just like you would a guitar, okay? And it's going to oscillate up and down like this. Do you have a good conception of what this is? Do you understand what my picture is trying to illustrate? Yeah. Right? So at any moment in time, if you were to freeze it, you would see a wave that looked like maybe this one here, right? Yeah. If you wait sometime later, right, half the period, you would see that it looks like this, kind of the opposite of that wave, right? Yeah. Does that make sense? Yes. Yes? And so it goes back and forth. So these things are going up and down and up and down and up and down, but it's not traveling, right? Traveling waves are different, okay? So that's what we're going to try to understand. And normally we would use it for our wave. We'd say things are equal to the cosine, right, of kx minus omega t, right? Well, because of these fixed points, we're going to actually use a sine wave, right? Because we want to fix it here at the ends, which means that, remember what a cosine looks like at the end point. If we call this x equals 0, cosine would be up here, right? Yeah. Well, this point is fixed. It can't move, yes? Yes. Nor can this point over here. Okay, so we're going to call this x equals 0. We'll call this x equals L, okay? So if this was, say, a guitar, right, this would maybe be the nut, and this would be the bridge, right? Yeah. So L is kind of fixed. It's one of the constraints that go in. And so what we're going to do is we're going to investigate these standing waves. And we'll start by trying to figure out how do we make such standing waves. Remember the method of images, or the virtual image that we talked about last lecture, or maybe it was the one before that. So I said that if this is a traveling wave, it's going to reflect off of this wall, right? Yeah. And we can imagine that reflection by merely kind of extending. Let's see if I can maybe use a different color for these. I'm just going to extend this wave, okay? Out like this, right? And this wave, I'm going to think of as a traveling wave going this way, yes? Yeah. I'm going to do the same thing on this side. Extend this wave. And this is a traveling wave going this way, right? Yeah. So if we put a traveling wave inside this cavity and we allow it to interact with this wall, it's going to reflect. And we can imagine that reflection as being the superposition of this virtual wave over here and this right-going traveling wave here, you see? Yeah. And the same thing for the other side. If we look at it from this point of view, maybe in this case we're going to think of a traveling wave going this way, okay? And its reflection that's taking place here will be something we can describe as a superposition of this virtual wave and this right and left going traveling wave, okay? Okay. And so it turns out that's exactly how a standing wave is formed. Right, that y is equal to 2 parts. We'll call it y plus and y minus. So y plus is just going to be some a. I'm going to actually write it as a over 2, and that will become apparent in a minute. A over 2 times the sine. Again, why am I using a sine wave instead of a cosine wave? Well, because I want it to be 0 here at these boundaries, okay? And a cosine naturally at x equals 0 would be 1, right? So I'm going to use a sine wave who is 0 at that boundary, okay? Remember, sine waves and cosine waves are closely related, right? They're complements, okay? So sine of kx minus omega t. So this is a traveling wave traveling to the right, okay? We've already dealt with these. We're familiar with them, right? This is a right-going traveling wave. And then y minus is going to be a over 2, same amplitude, sine of kx plus omega t. And the plus omega t is what makes it a left-going traveling wave, okay? So a standing wave is a superposition of 2 oppositely directed waves, okay? So we can simplify this expression using a trigonometric identity. I know how we love trigonometric identities. The trig identity we're going to use is right here. I want the identity sine of alpha plus beta, which is equal to sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Get a little crowded there. Okay? You guys remember that trigonometric identity?
I think so.
Sum of two angles identity, I guess they're called. So I'm going to use this identity on each of these terms. Okay? So first I want to do the y plus term. Okay? That's this part here, right? This is y plus. If I expand this using this trigonometric identity, I'm going to get a over 2 times the sine of kx times the cosine of minus omega t. Okay? Plus the a over 2 again, cosine of kx times the sine of minus omega t. Right? Those are my two terms. But let's remember that the cosine is an even function, which means that the cosine of minus omega t is the same thing. It's equal to the cosine of positive omega t. Okay? So I can just get rid of that right there, not worry about it. It's not going to change the sign of anything. The sine of minus omega t, though, this is an odd function. So the sine of minus omega t becomes minus the sine of omega t. Okay?
Okay.
So that means that if I get rid of this minus omega t here, I can replace it with minus the sine of omega t. So I'll just scratch that out, and I'll replace this plus with a minus like that. Okay?
All right.
Make sense?
Yes.
Now, underneath it, I want to write y minus. I'm going to do the same thing, but to this term. Okay? That's a little bit easier because there's no negatives in here, right? So that's just going to give me a over 2 times the sine of kx times the cosine of omega t plus a over 2 times the cosine of kx times the sine of omega t. Yeah, looks good. And I want to add these terms because remember this is y plus plus y minus. That's y, right? So if I add these, right, this term is identical to this term. So I have this minus this, right? When you add these go to 0, and all you're left with is these two, right? So you have a over 2 sine kx times cosine omega t plus a over 2 sine kx cosine omega t. That's just equal to a. So we'll write y equals a times the cosine of omega t times the sine of kx. So that means that we can replace this whole thing, right? I'll put it right here, I think, with a times the cosine of omega t times the sine of kx. Does that make sense?
Yeah.
You see now why I chose to use a over 2 instead of a, because if I'd used a, I'd have 2a here, right? So when I drew this, I didn't quite draw it correctly because what we should really be considering are waves that are half this amplitude. So it's really more like this. Half the amplitude of this wave. Same thing on this side. I've gone way too. Something like that, okay? I notice it's not perfectly symmetrical, but you get the idea. These virtual waves are actually half the amplitude of the standing wave that's going to form in the center, okay? So we can now think of the condition for which these standing waves will form, right? Notice that we have to have a node. A node is a place where the displacement is 0, okay? So we have a node here, yes?
Yeah.
We have a node here. Those are fixed. Those can't be changed. I just happen to put a node here so it looks more wave-like, okay?
Yeah.
But the way you can think about these are called normal modes, okay? So I take a cavity or some fixed points in space, right? Like the bridge and neck of the bridge and nut of a guitar, right?
Yeah.
And I try to fit sine waves in there, okay? But only sine waves of a certain wavelength will fit, okay?
All right.
So there's a node here in the picture that I've drawn. So I very well could have made this x equals L right here, right? That would be the kind of the longest wavelength that I could fit in this thing, right? Do you see what I'm talking about? It's just kind of an exercise in trying to fit sine waves inside of a cavity. So let me just do a quick. So if this is my cavity length, and I know it's got to be 0 here, and it's got to be 0 here, well, I could obviously get something that looks like this in, right? That's, again, not the greatest artistic skills here. Yes?
Yeah.
That's like whatever this wave is, right? This is only half of its wavelength, right? I could draw the other half over here, doesn't it? Right?
Yeah.
Or I could take another wave and fit in here, like I did drew up here. Just that, right? That would fit, yes?
Yeah.
I'll draw in a moment a complete set of these. But I just want to formulate this picture that we're trying to get here for this, right? That we're trying to fit sine waves, but only certain sizes of waves will fit in there, right? Because it has to have a node at the point x equals 0 and x equals L. All right? And that turns out to be a very interesting situation because a lot of the things that we'll see in physics, like take quantum mechanics, for example, if you're trying to understand the reason for the quantization, right? Why is it that energy only comes in these certain discrete allowed states and not any old energy, right? It's related to this phenomenon right here, right? Of fitting waves inside fixed cavities where they have to have nodes at these 2 points, x equals 0 and some x equals L, okay? That's a completely different kind of wave when it comes to quantum mechanics, but the idea is essentially the same. If you want to build a laser, right? Lasers require laser cavities, right? They fix the wavelength, right? Because you have a certain size cavity. Now, so I suppose we could more correctly write this as follows. Let me just change what I wrote here to cosine of omega sub n times t times the sine of k sub n times x. So what's going to turn out to be the case is that omega and k, which are related, of course. If you know one, you know the other, right? They have to have a particular relationship, and we're about to discover that real quick. So let's now set the boundary condition for this. So what does a boundary condition mean? It means, so BC for boundary condition. We know that y at 0, comma t, any moment in time, right, and y at L at any moment in time have to be equal to 0, right? So if I look at, say, this portion of it, cosine omega t, let's look at the first boundary condition, right? So when does a cosine omega sub n t times the sine of k sub n times 0, because x is 0, equal 0? Well, always, because the sine of 0 is 0, right? So that's already set. That's part of the reason why we chose to start out with a sine wave instead of a cosine wave, okay? So that doesn't give us any information that's useful. How about this one, this boundary condition? Saying that the displacement at this position, x equals L, has to be equal to 0 as well. So let's set that. We get a times the cosine of omega sub n t times the sine of k sub n, and x here is equal to L. L equals 0, right? Well, if I divide both sides by a cosine omega t, it still stays 0, and I get that the real condition is that the sine of k sub n times L is equal to 0. When is that ever the case? Well, that's when k sub n times L is equal to any multiple of pi, right?
Yeah.
Then this will be equal to 0. So if n is equal to pi, what is the sine of pi? That's 180 degrees. 0. Sine of 180 degrees is 0. What about 2 times pi? Well, that's all the way back to 0 degrees again, right? What's the sine of 0 degrees? No, not the cosine, the sine of 0 degrees.
0.
0, right? Look at it. Look at the graph of a sine wave, right? Sine of x. Here is x. Start at 0, go out to 2 pi, right? What does it look like? Starts at 0, going to come back to 0, right? So where is it 0? Once it's 0, it's x equals 0. It's 0 at x equals pi. It's 0 at x equals 2 pi. Therefore, it would also be 0 at x equals 3 pi, which is going to come back to this point here, and 4 pi, which is really just this again, right?
Yeah.
So that's when sine of KL is going to be equal to 0, which means that this is the condition that we get, right? K sub n times L has to equal to n pi, which means that K sub n is equal to n pi over L. That's terrible looking. Let me draw that a little nicer. There. Okay? So in terms of the wavelengths, since K is just 2 pi over L, implies that lambda sub n is equal to 2L over n. So if you want to know what the acceptable wavelengths that will fit inside this cavity are, right, just take the length of it, double it, and divide by n, where n is any integer. 1, 2, 3, 4, okay?
Okay.
Does that make sense?
Yeah.
let me draw a picture to illustrate this. So this would be the longest wavelength that we can fit into this cavity, okay? So here we would call this L over 2, right? Where this, of course, the cavity length is L, right? So don't forget that. This cavity length is L. So this would be the n equals 1 wave, okay? We call this the fundamental. You've got the 2 nodes at the end, but no additional nodes in the wave, yes?
Yeah.
The next wave that you can fit in, right, is this wave here. And this is going to be 2 times lambda over 2, which is just lambda. You see that?
Yeah.
I could write it as 2 lambda over 2. It might make it easier to see what's going on here. In this case, this is the n equals 2 wave, and we call this the second harmonic. Second harmonic. Okay?
Okay.
This one, and you see it only has, it's got the 2 nodes at the end, of course, but also an additional node right in the center. Yes?
Yes.
This one, right, what is this? Well, this is 3 lambda over 2, right?
Yes.
This is the n equals 3 condition. So you see where the 2 is coming in, right? So this is like 1 lambda over 2, 2 lambda over 2, 3 lambda over 2. This, of course, is the third harmonic. Okay? There's a 4th harmonic and a 5th harmonic, etc. As many harmonics as you want. And these harmonics, these are the modes that are valid solutions to the wave equation. So remember I said that when you solve the wave equation, right, you can create, you can create a superposition of modes, or a superposition of any wave that is a valid solution to the wave equation. Well, in the case of a cavity, right, these are the valid solutions to the wave equation. It has that additional constraint, okay? And so you can write any wave on that, let's just use string as an example here, right? Any wave on that string can be written as a linear combination of any of these modes. And so the timbre, right, which is the unique sound that an instrument has, is some combination of all of the modes available on the string. There's an infinite number of them, right?
Yeah.
But not every wavelength is allowed, you see? And so it's that combination of those tones, right? The first, the fundamental, the second harmonic, the third harmonic, etc., which give the characteristic sound that a particular type of instrument has. That's why, you know, a violin sounds like a violin and not like a cello, not like a guitar or not like a piano. These are all stringed instruments that have these conditions set, okay?
All right.
Since these are strings, right, let's just take a brief look at, I said that K sub n was equal to n pi over L. This was our condition, right, for the wave equation to be satisfied for a standing wave, right? And omega over K is equal to the velocity, right?
Yeah.
That means that omega, we could write omega sub n is equal to the velocity times K sub n, which is equal to, well, K sub n is just n pi over L, and V, the velocity for a string, for example, would be the square root of the tension in the string divided by the linear density of the string, okay? So you could use this, for example, to, you know, design a musical instrument. If you wanted the fundamental to be, you know, so n equals 1 would be the fundamental. If you wanted to design this to be a particular frequency, this is how you choose it, okay? You set the tension. This affects your string type that we actually did a calculation like this earlier, right, for a guitar string. I'm not going to repeat that, but this is essentially the reason why we can do that, okay? So let me just rewrite the equation we started with, right, the sum of the 2 sine waves, but introduce this constraint for the wave vector, wave number. So it would look like y equals a over 2 all times the sine of n pi over L times x minus vt plus the sine n pi over L times x plus vt. And so that is kind of the general wave equation for a standing wave. Okay. Now I left v in because you could these could be acoustic waves, for example. Okay. This could be a pressure instead of just a displacement. And so now the cavities we're thinking about are the cavity like horns and things like that, right?
Yeah.
But horns, if you think about it, they don't have two closed ends, right? They've certainly got one end, the part where you start blowing, right? But then the other end is open, okay? So that's a different boundary condition. It gives slightly different equation for that, okay? So we've already looked at the two fixed ends case, right? That's what I'd call a cavity of some kind, right? But there's the what they call the free end or open end solution as well. And how would we approximate that with a string? Well, I can imagine that I've got a fixed end for my string. I'm going to make my string actually a thick rope like this, okay? And we'll say that its L is its length, okay? And I'm going to attach to it a really small string, right, whose density, linear density, is approximately 0, okay? So we did that with reflections the other day, right? We talked about creating a wave on a thick string. When it gets to this interface with a really light string, what happens, right? The reflection is no longer inverted. It comes back in the same orientation that it came in at, right? Remember that?
Yeah.
Yeah? So this gives us a slightly different boundary condition. What the wave will look like, if I were to draw the wave, is at this location L, it could be, do it like this. Basically, now the condition is that we can have a maxima or a minima there, okay? So we would get that the sine of k times L, right, where this, of course, is L, it has to be equal to plus or minus 1 instead of 0, okay? Plus 1 for a maxima, minus 1 for a minimum, right?
Yeah.
And so when does that happen? That will happen if k sub n times L is equal to n pi over 2, because pi over 2 is when a sine wave is equal to 1, right?
Yeah.
Yeah, so any integer n times pi over 2 will satisfy this. So that gives me that k sub n is equal to n pi over 2L. So very similar to the condition we had up here, right? We would just modify this for a free end to, instead of having n pi over L, we'd have n pi over 2L, you see?
Yeah.
So it just changes what wavelengths are allowed on the instrument. But this would be adequate, I think, for like a horn, like a cornet or something like that. Because you've got the open end, right? Which is like the really light string, okay? And then pianos and guitars and stuff like that. I think pipe organs, right? They're fixed by a close. Well, I'm not sure. Maybe it is an open end because it's got the little opening at the end there. I think all horned instruments are probably open end. I'm not sure. I'm not a music expert in this regard, but that's the idea of standing waves, though. Turns out to be extremely important. This was definitely important for like quantum mechanics in the work that Planck did on understanding blackbody radiation. And of course for musical instruments and stuff like that, and for a variety of reasons. But standing waves are a pretty neat concept altogether, okay? Does that make sense? Seem logical, or is it confusing? Any questions about this material we've covered? See if anything else I want to say about it? I think that's it. You look like you have a question, so you can ask if you want. No? Yeah, well, again, so it's two traveling waves traveling in opposite directions, right? We can either write it in this long form like this, or we can write it in the sine times cosine form that we derived earlier, okay? That one's a little easier to work with to get the boundary conditions set. But really, this is what we have going on here, okay? And it forms a standing wave, okay? All right, next time I think we'll do Doppler shift, and that will pretty much wrap up this semester. The next semester we'll start with thermodynamics, so electrodynamics and maybe some cosmology and quantum mechanics too, of course. Okay.